Okay, so today we're going to be doing another distillation column, but this time we're going to be involving some liquid dynamics. So I'll go ahead and read the problem statement here. We're going to be deriving, I actually have a little checklist or kind of a list of the main things happening in the problem statement, but basically going to be deriving two differential equations, one for um, the liquid molar holdup and mole fraction, or I'm sorry, governing the rate of liquid molar holdup. So it'll actually be one for moles. We'll do a molar balance, and then another one for a component mole balance for the more volatile component. So involving the mole fractions of each stage. So nothing crazy. Um, and we'll end up having to do a sort of product rule, and we'll write out those expressions here shortly. But going on with more of what the problem's asking, some initial conditions we have. Well, we have constant molar flow rates. So again, that relates to the heat of vaporization not changing with composition. Kind of went over this already in a previous video, so I won't go into too much detail here. That was the video where we did our first distillation column. So this is our a second distillation column we're doing, but some things have changed. So that's why I'm going over the details. Um, and another one is we're ignoring vapor dynamics. So we also did this in our last distillation column. And there's actually two reasons why we can ignore the vapor dynamics here. One of them being the related to the energy density of the vapor flow rates. Well, the energy related to that vapor flow rate is much higher relative to the liquid flow rates of the distillation column. And what this means is that as we change the vapor flow rates, well, that's associated with a change in temperature for the liquid flow rates. But this change in temperature is pretty much instantaneous as it's transferred from the vapor to the liquid, since the energy of the flow of the vapor flow rate is much higher than the sensible heating of the liquid. So that's one reason. The second reason why we can ignore the vapor dynamics is also kind of due to a molar density. Uh, Again, if we increase our vapor flow rate, you'd imagine that we're introducing more moles to the system. But remember that the volume of the vapor in the column is already quite big. So introducing more moles to that already existing pretty large volume, well, scale of that is pretty much something like 1 to a 1,000th of what we're doing compared to a liquid, where if you do increase the liquid flow rate, that is a pretty significant amount of moles you're adding to the distillation column. So those are just two reasons why that negligible vapor dynamics is actually a reasonable assumption for at least our case. And we're also saying that the vapor flow to the condenser is perfectly controlled. So that's a perfectly controlled or a controller at our reboiler, in which case it's instantaneously changes our vapor flow rate throughout the column to match, say, the sum of the reflux. So what we're returning, the liquid flow from the condenser, and our distillate, which we're picking up. And since that's instantaneous, and it's matching that sum of what's coming out, well, if in equals out, well, you'd imagine that the molar balance for the condenser is pretty much zero, since we're saying we have perfect control there. What else? Oh, I kind of skipped over this, but I have another condition here written VLE, so that's vapor liquid equilibrium. And if you remember, this is just how we've described vapor liquid equilibrium, or yeah, vapor liquid equilibrium in the past. This concept of relative volatility represented by alpha. So again, if you remember, this was the K values. So K values were a equilibrium proportion relating um, the vapor mole fraction to the liquid mole fraction. So we'd have y1 and x1 for component 1, and then obviously y2, x2, or in other words, 1 minus y1 and 1 minus x2. And this is for a binary mixture. So of course you'd imagine it gets more complicated if it's not a binary mixture. But again, in our case, we're assuming it is, and that if we have constant relative volatility, in which case at equilibrium, these ratios, these proportionality factors are equal to each other, um, that is how we're describing our equilibrium. So this will be some constant, something like I think it's 2 in the next part, where we actually code this out. But this video is only going to be about deriving our expressions that we're going to be using. So yeah, again, this relates back to Raoult's law. I won't get into it much here since we won't. I mean, it's not asking us to derive it here, but I will definitely go over this once more since we're definitely going to use this again in the actual code. So I'll go ahead and derive that in the next video. I think that's all it for the conditions. The other thing to note here is this idea of holdup. So again, going back to the problem statement, we're going to be monitoring, or I guess simulating our liquid flow rates with this idea of the Weir formula. So again, you can kind of see the Francis Weir formula here. It's this idea that we have some sort of constant W, and this idea where we take the power of this expression to 1.5. Kind of read up on this more, it kind of gets an increasing more in complexity as you kind of add in more variables and more parameters. But essentially, this is this expression L equals W times the holdup, the difference in holdups to the 1.5 power is how we're simulating that liquid flow rate. And you might be asking, well, what is holdup? We'll go over that. I mean, I'll just go over it right now, I guess. So, I guess I could just draw it out. I'm trying to think. Yeah, I'll just draw a smaller one, and then I'll draw the distillation column again. So for holdup and each stage, it's not letting me scroll over. Here we go. So in each stage, you'll remember we'll have our weir. So the weir is this little ledge here that kind of holds up the liquid before it overflows. Then obviously you have your liquid. I should have chosen not blue, but oh well. So we have our liquid that's kind of holding up, again, hold up at each stage. And then as it overflows this weir here, it's associated with some height, and it'll overflow down, obviously, into the next stage where the cycle repeats. And obviously we're having multiple stages across our distillation column, so it'll all overflow. So again, this overflow, this idea of an increase in height from the weir, is associated with our liquid flow rate. And if you can kind of see, well, obviously if it's overflowing this minimum holdage of, I don't even know if that's a word, but this minimum amount in each stage, you can kind of understand and see why you're going to have more flow coming down versus something that's just tipping over the edge right there. So that's the idea of holdup. And from that, well, our expression we use, so let me just write it here. I believe it was our liquid flow rate, our W's, some experimentally determined value. And then we have our holdup where we have our moles. This is kind of going into our derivation, but I can go ahead and use it. I'll go ahead and use it now. So we have our moles minus our minimum holdage. I think we called that like our M holdup or something like that. So this is the minimum amount we're going to be using to describe when it just hits that Weir height right there. And again, M just by itself is the, well, you can kind of guess the number of moles associated with that extra height. So yes, that extra height is associated with moles. And the reason we know that is, well, if we have a height, well, we can multiply it by this area here. And multiplying by an area, well, that's just meters times meters squared. And that gives us meters cubed, which is volume. And what do we do with a volume? Well, something we can do with that is we multiply by a density. So that's just mass over volume. And we get our mass, so density multiplied by density. So let's just keep track here. We did height times an area to get volume times a density to get mass. And then now we're going to divide by our molecular weight. So that's just inverse of moles and some mass. We divide by our molecular weight. We'll have moles. So pretty self-explanatory. kind of imagine a kind of straightforward calculation, but obviously there's more factors going into this. Something like viscosity. If we have obviously a more viscous liquid, you'd imagine we'd have a slower liquid flow rate, and all those factors, including the one I just calculated right now, relating to the moles, and if it is relating to the height, is all included in this uh, W parameter. And again, that will be experimentally determined. Um, yeah, don't think I'm missing anything else. Oh yeah, I forgot my 1.5 power here. And I believe we are ignoring right here. It ignores a typical considerable bubble volume. So as you imagine, again, from our distillation column, there's actually vapor coming up through here, and obviously vapor leaving. But as the vapor increases, or vapor flow rates increase with our reflux ratio, well, obviously if we want to take out more, we have to supply more vapor to condense it. If we increase that vapor flow rate, obviously there's going to be more vapor entrapped in there. And obviously this expression does not account for that, and we are omitting that, which is pretty, I don't want to say reasonable, but significant factor to include. So again, this expression does not account for that. I think that's all I wanted to say here. Yeah, I guess we can just go ahead and derive it. I guess I'll just draw out the distillation column, and I can kind of just break down the stages as we go. These two differential equations that we're deriving actually apply to each stage, but you'd imagine for the condenser and the feed, as well as the reboiler, those will have a slightly different expressions for our two differential equations. So I guess more on that later. Let's go just like this. So we have a feed. Oh, let's go a little further down. So I'll just, I'm a little lazy, so I'll just draw 5. So I'll have a big one, and this can be our N. And then we have our condenser. And this will be, maybe I'll draw one more. So you can kind of imagine, so this would be like N minus 1, and then we have 0. I'll move those to the side. And then N. Let's go this. So we have N, obviously, N plus 1. And then we have our last stage, I'll just call it big N. We have our feed going in, so some composition of the feed, and also the quality. This isn't really important for the derivation, but just kind of going over what we had before. I'll actually just put all those together. I think I could have just drawn this out earlier, but that's okay. We have our distillate, associated with that some liquid composition, and our bottoms, again, another liquid composition. And of course, this is all done for a component balance of the more volatile component. So obviously you'd expect a higher liquid distillation composition than the bottoms. And obviously increasing separation as you go up the stages. I think the last thing I want to write is probably go the vapor flows. So yeah, let's just go vapor up, bar denoting obviously below the feed, and then liquid going down, liquid L bar denoting below the feed once more. And why not, we can just draw all our arrows. Yeah, feel free to put this in double speed, since I'm pretty slow here. And I can draw our coils, since why not? Cooling coils and our boiler coils. Okay, so none of this is actually going to be used. Well, I'll actually kind of zoom in, or I guess redraw again, this middle stage. So kind of putting it in terms of n stages, so you can apply it to any number of stages. So I guess kind of enhance on this. This isn't really a um, I don't know, zoom in. This isn't a feed or anything. It's not going anywhere. I'm just ev- eventually I'm gonna be just drawing what I drew up here, essentially. Actually, why don't I just copy this? It's actually not a bad idea. So I'll go ahead and I might just take it, honestly. So yeah, I'll just do that since it's already drawn. Remove some of the stuff here. Um, yeah. All right. So yes. Go ahead and do our mole balance. So kind of drawing this out. Well, what do we know? Well, we have our flow rates. Obviously, those relate to our mole balance, and we'll just draw those out. What color did I use? So pink, purple, and blue. I can't use blue again, so whatever. So vapor going in. If this is the nth stage, and this is n+1, and this is n-1. So we have vapor going up. That is a little too big. We have vapor going up, and that is from the n+1 stage. And obviously vapor going up. Now this is from the current stage. And the other thing we have is, I don't know what color. Let's go pink. We have liquid coming down. So this is our liquid. Maybe green would have been better. So our liquid coming down at our stage. And obviously, maybe I could move this a little bit. A little disorganized today. So vapor coming up, and then obviously liquid coming down from the stage above. So these four are the things we're going to be considering. These four flow rates are the flow rates we're going to be considering for our mole balance. And obviously, if we had a feed in here somewhere, I think I had it directly in there. So if I had a feed going straight in, it'd obviously just be the feed flow rate going in. And obviously this is associated with a mole fraction. Obviously the other flow rates will be associated with a mole fraction once we do our component mole balance for the more volatile component. I think that's all I want to do. What might bother you, and this is kind of an aside, is I stuck the feed inlet, I guess the feed pipe straight into the stage. And what you'll notice, at least with our ideal scenario here, if this is all liquid, all vapor, or both, it doesn't really matter where I put this. I could have put it up here. I could have put it down here. Essentially, the only thing this affects is if there's liquid, it'll go to that stage. If it is directly into a liquid stage. So again, liquid will just fall down. As you see in our column, liquid just falls down, vapor just goes up. So in the end, it doesn't really matter where I'm putting that feed, as long as we're consistent as of which stage we're putting it in, and we know what's getting added to that. For this mole balance, it doesn't really matter if I include the feed. I think in the actual coding, we'll have it separated out. Like I mentioned how the feed, condenser, and boiler will be slightly different from what we're deriving here. I might just do that separately here as well. So yeah, I think I'll do it separately. Like I'll have a feed. Um, I mean, in the end, what we're going to do is we're gonna have an array of our moles, our M. So it's gonna be a list of our array or list of moles of our stages, all lined up left to right. And what we're gonna be doing is filling in each of those stages with our expression. And then for our special cases like our condenser, boiler, and feed, we'll have to kind of manually code that in what the correct expression is, since it won't be the same. So I'll just go with the original expression for now. So just based off our diagram here, let's sure we're recording. Okay, so actually now doing our problem here, let's start with, we have our mole balance. So this will be a change if our moles in n, the stage n, with respect to time. So we have our four flow rates. Let's do our liquid flow rates first. So we have our liquid, since we want to add to this. Yeah, so liquid flow rates, ln -1. So the flow rate coming in from the stage above. And then now we're going to be subtracting our liquid flow rate from the current stage as it falls out. With that, we have our vapor flow rate coming in from the stage below, and then we are subtracting our vapor coming out from the current stage. So, not too bad. For the feed, I guess I could do a parentheses or not. Let's do something like if at feed, it'd simply be, well, we have our expression here, our change in moles at the stage. We simply, and this is in place addition, kind of cheating here, so I don't have to rewrite it, but you'd be adding to itself. I think we used this before in a previous video, but essentially this is the same thing as saying we're adding on, or rewriting the original one to add on itself plus something else. So that's the same thing as I'm going to add on the feed as a flow rate. So not too bad there. If I really wanted to, we could put an F here, but I'm just separating it so I don't mix it up when I come back, look at this when we do our code. Yeah. Then what you can imagine is for our component mole balance for the more volatile component, we will have, we are introducing our mole fractions. So with that, we have the change of moles at our current stage for the more volatile component at the current stage. I'll write it with the 1 for now, so we're crystal clear that this is the more volatile component, component 1, as we always do traditionally in naming the more volatile component with 1. That's just a standard of how we've been doing it, but you'll see me take it away here as I kind of do some substitutions so it doesn't get too crazy. It doesn't look too messy. Yeah, so it's literally just we're matching up the molar fractions with their current stage. So with liquid flow rates, we have obviously our liquid mole fraction at that stage. So again, these molar fractions will be different. So that's why we have to make sure we match each stage that they're coming from. So do something like that, minus this stage at the current stage. So again, 1 at the current stage. So, and then obviously with vapors, we have our vapor mole fraction, liquid mole fraction earlier with the liquid flow rates. So now I'm just doing the exact same thing, matching them up once more. Nothing too crazy again. The liquid mole flow rate times the liquid mole fraction of our current stage. Yeah. So actually, we're done. I guess if at the feed we can we'll have same thing. I don't know if it gets confusing. Honestly, I could just write it here, but I'll write it both ways since why not? So if at the feed I do the exact same thing, but now since we have mole fractions, I'm just gonna add the component, whatever composition we're putting into the feed. So now that's a molar fraction. Yeah, I guess I said I was gonna put it here too. So it'd look something like that if we had the feed. So I'm just gonna omit it for now since it'll be separate when we're coding it. Again, I don't want to confuse myself. So we're not actually quite done, but that was pretty much the hardest part. You'll notice here though, we are taking a derivative on the right hand side or left hand side here for our second diff EQ. This is derivative of two dependent variables. We have our moles and our mole fractions. And you'll also notice that we actually already did our derivative of our moles. So if you kind of see what we're going to be doing here, this is a product rule. We've done this before with our differential equations. I think it was an energy balance for a previous video. But yeah, product rule, gonna do that right here. Break that down so we can just have a derivative of our an expression relating just our mole fraction. So I'll go ahead and get rid of our ones here, since we all know now, or we should know that it's the more volatile component. So I'll go ahead, try to write this in a more clear way. So this is moles and mole fractions. So we do product rule, we have our moles, and then change of our mole fraction plus, and now we have our mole fraction out and derivative of our moles. So that's all we needed to do. And if we want to, again, we want to have a differential expression for our mole fraction, just like I mentioned there earlier. What we need to do is just isolate that. So that's not too bad. Actually, we have everything we need. We actually have, again, I mentioned we already have this from earlier, right here. And we actually wrote out, I'll just keep that for now. And we actually also wrote out our, before we did the product rule, we have our original expression relating both of them. So if we want to isolate that, that's pretty easy. So I'll go ahead and rewrite that. It'll be something like, let's see. So we have the change in the mole fraction by dt, and we have, well, this is our constant, so we're going to divide it across the other side. Well, it's not a constant, but it's a variable we can move to the other side. That's our moles per stage. So once we move that to the other side, we're going to be subtracting these two expressions. So maybe, I don't know if this is worth slowing down, but I mean, essentially we are just isolating. Oh, that's erase. We are just isolating. Well, I already drew it, but it's the one in red. Oh man, what's happening? Just this. So hopefully it's pretty self-explanatory. Like, we have all these expressions already, so I won't bother to rewrite everything. So if we divide mn to the other side, the moles per our current stage, we have our difference between these two. So go ahead and write that out. It is this. And then we have to subtract our second expression from the product rule. So that is just minus xn dmn dt. And, well, we've written both of these out already. I guess it's, you know what, why not? We can write it out. So our change in mole fraction for the current stage equal to 1 over the current moles of that stage. And actually, yeah, I can just copy this. I don't know why I'm reluctant to rewrite it. So we're copying. We already did this already. I'm just substituting everything we had in. So again, you'll notice that, well, again, we have all these expressions already. I'll go ahead and put this underneath. So something like that. Hopefully that's not too confusing. So we have minus xn. And then now we have our entire expression now just for the flow rates. Actually, I could have just wrote that down, but that's fine. And again, you'll notice if we had the feed here, I would just be copying down the feed. So parentheses, and yeah, if I had the feed, well, here it would be plus zf, and here it would be plus f, the parentheses. So hopefully that's not too confusing. When you have the feed at the feed stage, that's the only difference between any other stage. That's not the boiler and the condenser. So pretty easy. Now with the boiler and condenser, we do have to look at what's going in those stages. I know what's the best way to look at this. Maybe up here. So if we are at the boiler, actually let's do the condenser. So if I had that condenser, you note that there is no vapor stage going up. Actually, this stage is tiny drawing I had. So there's no vapor. Oh, there's no vapor going up. It's just vapor going in and liquid coming down, and then the distillate of what we're taking out. So in the problem statement, I believe we already said that the vapor is perfectly controlled to match the sum of the liquid coming down, our reflux, and our distillate. So if it's perfectly matched, that means, well, there's no change. The moles of our the moles of that stage um in the condenser. So essentially what that means is, well, the MGT has to be 0. And this should make sense since we have our vapor flow rate going in. It'll be from the first stage, if we number 0, 1, 2, 3, obviously. And then, as we know, this is equal to our liquid coming down, our reflux, plus our distillate we're taking out. So if we want to make sure this expression is true, well, we just need to isolate everything so that it equals 0 for our mass balance. So I guess I'll just move everything to the left. So it'd be V1 minus L0 minus D. Pretty simple. I believe in the next video, the next parts include something about the distillate where we're going to be ramping up that as a function of time. So we'll have to indicate, actually this is the main difference between the condenser and the boiler, reboiler. We'll have to kind of have it as its own separate function rather than defining it as a constant, which is what we do for the bottoms in our reboiler, where it's just a liquid flow rate coming down. More on that later. I'm sure I'll go over it again in like an hour 30 or whatever I normally do. So at the my voice is getting hoarse. At the reboiler now, oh yeah, I guess I should also do the mole fractions, so I guess I'll move this up a little. So, I mean, with the mole fractions, it's pretty self-explanatory. You'll notice that they are different from, well, actually, our differential equations in general are very different from our ones we derive for each stage. Essentially, what we have, well, I mean, you can kind of cross it out here. We have V1L0D, so that's a vapor from the stage below. So vapor from the stage below would be this one. So no vapor coming out, no, there is liquid coming down, and there's no liquid coming down from the stage above. So we do have these two, but we do have to include our distillate. So that's why I said it was kind of a special stage, since they aren't different. They are different from any other stage. And it's kind of the same thing with our, I mean, I don't even think we have to do this for a molar fraction since it doesn't change if it equals 0. But if you did, actually, I'm not too sure about that, but I'm going to go ahead and say it now, so I'll do it for the sake of saying it. We have our x1. But now this is, I know earlier we had a comment about x1 being, I took out the x1s in our expression here just to avoid rewriting them. I think I just ended up copying them, so I didn't have to rewrite it. But here, x1 is not for the more volatile component, even though it technically is. Now it's also talking about the stage, so hopefully that's not too confusing. Then we have our, this should be a y. I don't know why I put an x there, so it's a y. Then x is our liquid mole fraction, so that's what's associated with our liquid flow rate coming down from the 0 stage or the condenser. And then obviously with our distillate, we have a distillate composition. So not too bad. So since it's 0, I'm pretty sure we don't have to do this, but I did it just in case. Now the reboiler is where it does matter. Believe again with our, when we're coding this out, we'll have an array of vapor and liquids, which we add or subtract depending on our mole balance here, and we'll do indexing for that, as we've done many times before in the past, to relate to our, again, our kind of, I don't want to say bigger index, but it's the same number of elements, but that will go into our calculations for the molar balance and our mole fraction balance differential equations. So with the reboiler, nothing crazy, pretty much same idea. Though in this case, they do not equal 0 since we have liquid dynamics coming into play. That liquid is not perfectly controlled. Again, it's changed by our liquid dynamics following the holdup from the Weir formula. So it's not going to be equal to 0 as it was at the condenser, but we do know our mole balance relating to the reboiler down here. Again, this tiny drawing, we have our liquid coming in from the top, I guess you could say big N plus 1, and then vapor coming up from the boiler, so that's just Bn. But yeah, I guess we could do it for big N. I don't know why I wrote N here when it's just 0. So that might have been confusing there. So this is just for the condenser. And in this case, we can use big N. So, what did I say? Liquid going in from the stage above, N plus 1. Or is that N minus 1? N minus 1, right? Yeah, because big N minus 1. So big N minus 1. Big N minus 1. And then we have vapor coming up. So that's, well, we're already in our expression. So I'll write it up here. It would be liquid coming up from the stage above. N plus 1 is equal to into must equal out. So in is our liquid, out is our vapor at stage N, plus our bottoms, so bottoms, which is this B. So if we want to do a balance on that, we just move everything to the side. So I put N plus 1 again. Why did I do that? Okay. Yeah, N minus, and okay, N minus 1 since we're going up. Okay, sorry about that. Minus Vn minus B. So we're just moving everything to the side. So we're noting our change. And the reason why this is 0 is because this statement holds true. It's a perfect sum because it's a perfect controller. We have the same expression here where we moved everything to the left-hand side, but this technically isn't true since I believe it's not true. Not until we hit steady state anyway. So we will have a change in our moles for the bottom stage. But when it is true, then that's why we're trying to zero all of this out anyway. We're going to zero out our moles and our mole fractions, the change of those at least. With the root scalar, that's why we're writing it like this. So we isolate it and equal it to 0. So eventually it'll equal 0. So again, now it's the mole fraction, big N. You just simply match them up. So liquid mole fraction, oh boy, liquid mole fraction to liquid flow rate, subtract vapor mole fraction to vapor flow rate, and then our bottoms, liquids. That's a little clustered. I'll move that over. So yeah, we'll be coding this all out in the next video. I'm pretty sure that's all we went over. I kind of went a little overboard. I don't think this is supposed to take this long, but yeah, we'll be pretty much putting all these expressions in. Anywhere you see a D with an M or X, that's our moles and our mole fractions, and that's what we're trying to zero out with our root scalar, the change of those. So yeah, make sure I didn't miss anything here. So yeah, we just derived the differential equations and like kind of explain all the conditions we had. Yeah, next video we'll be coding this out. So kind of look over this, make sure. Again, with the feed, it's just nothing different from the original stages in the rectifying or the stripping. We're just adding a feed and our mole fraction. I believe I already showed that before and I erased it. And then we have our condenser and reboiler, slightly different, but kind of making sure we know what flow rates are going in and out and expressing them like so. We also went over the Weir formula, explained that, and then yeah, vapor liquid equilibrium with our constant relative volatility. All right, see you in the next video.